Morning, everyone. How are we doing? Questions while we wait for others to come in? Anyone? How are we doing? Morning, Ahmad. Laura's asking when the last web work will be released. It depends what we do tomorrow. So if we don't get far enough tomorrow, there won't be another web work. And if we do enough material tomorrow, I'll open up the last web work tomorrow. Yeah, I know. We don't have a lot of time to do it, but, well, we'll see. There might not be one, so let's not worry too much about it. Ranji, remind me what oh yeah, I remember the, yeah. So Ranji had two questions yesterday. I think we should discuss them. Suppose you have the following scenario. Suppose you have two equations of x, y, and z, right? So you can imagine the scenario. And, right, I mean, what do you have? You've got two equations, three unknowns. So imagine, theoretically, maybe isolating for z in the first one. So z is a function of x and y. Plugging that into here. So now you have just one function, just one equation involving x's and y's. So maybe you can solve for y as a function of x. And if you plug that back into the z, if you change all the y's to whatever function of x you found, then z is also a function of x. Right? So two equations, three unknowns, you can solve for two of the variables in terms of the third one. Any two that you want. This is a theoretical result. In the case that this can be done, right? It's not always possible, but theoretically, you might expect to be able to solve for two variables in terms of a third one, or the third one. Ahmad is suggesting you wouldn't be able to guarantee a unique answer. Well, that's the question. When are we able to guarantee that we can do that? And this comes to us via the implicit function theorem, which says that we can solve as long as the partial derivatives with respect to the variables you want to solve for are non-zero. So let's assume that this is correct. Prun, yes. I believe I posted a link to the final exam schedule on my courses. Prun is asking when the final will be. So I posted a link to the final exam on my courses. Have a look at that. For those of you who were experiencing difficulties with my courses, I think I figured out what the issue is. It's Chrome. There's something with the security. There's something wrong. There's something wrong. The website seems to be incompatible with Chrome. I opened it up on Edge, and it was working fine. So I think Chrome really is the issue. There's some incompatibility there. IT Services has been made aware of the situation, and I think they have contacted either the My Courses people or the Chrome people, but I mean, somebody's been contacted apparently. Yeah, so that's the idea, right? You might expect to isolate, let's say, for z as a function of x and y, plug it in, then you just get a function of x and y. So maybe you can solve for y as a function of x and then plug it back in. So y and z would be functions of x here. So Anna is saying the exam schedule says June 4th starting at 9. That's what it's going to be. Again, I have no control over that. They are in charge, and that's what it is. So what? So in that case, if y and z are functions of x, what is dy dx? What is dz dx? These are valid questions. And look at your functions again, right? F of x, y, z equal to 0. If you differentiate the whole thing with respect to x, with the understanding that y and z are functions of x. Well, you've got an x there. This is a function of x, and so is this. So the derivative, f1 plus f2 dy dx plus f3 dz dx. And if you do the same with the other one, g1, g2 dy dx plus g3 dz dx. And now you have two equations, two unknowns. So you can solve for dy dx and dz dx. And what? I think it's clear that dy dx is going to be negative f1, negative g1, f3, g3, over f2, f3, g2, g3. So g1, f3 minus f1, g3. There you go. And same for dz dx. How are we doing? Ranji is asking, why is it necessary to make y and z functions of x? It's not that it's necessary. It's that it's possible. It's possible, and the implicit function theorem tells you that it's possible as long as this denominator is not 0. Ranji is asking how we got this business. Somebody want to answer that? Oliver is asking, is the final a 72-hour exam or is it a 3-hour exam? It's both, right? It's a 3-hour exam where you have 72 hours to complete. Right? I mean, here I'm saying two equations, two unknowns, so you can solve for dy dx and dz dx however you want. You have complete freedom to solve here. How did I solve? What is this? Somebody want to answer that? Anybody know what that is? What did I do there? It does kind of link to the Jacobian, right? But no, I still don't see the answer. Anybody? Nobody? What about those of you taking 263? You should have seen that in 263. No, still not seeing the answer. No. Anybody? Those 263 people? Anybody? No? Kramer's rule. It's Kramer's rule. All right. So that's the idea. Let's say dz dx similar. Yeah, the 133 material that you've all done, right? How are we doing? Questions here? Anybody? Let's go back to this, what we were doing last time, namely polar coordinates. Let's draw a picture of what's happening here. Find the volume inside this and outside of that. What is this first thing? You recognize this, of course, as what? Anybody? You know what this is. A sphere of radius 4, centered at the origin. Right, thank you. And then what is this? Well, this is a circle in the xy plane, a circle of radius 2, centered at the origin. But there's no z specified. So it's that same circle stacked one on top of each other in the z direction. And what do you get? You get a cylinder. A cylinder of radius 2. So what are we looking for? We're looking for the volume between the two. Very reminiscent, if you remember in 141, you had this web work question where you had a cylinder, you had a sphere, and you drilled a hole through the middle. And what was so the center of the sphere is 0, 0, 0, correct? Meaning the origin. Right, this is the equation of a sphere centered at 0, 0, 0. So again, right, not very similar, but exactly that same question you had in 141, where you were drilling a hole through a sphere. Volume of, that's the issue a lot of people had on the web work. They tried doing the volume of the sphere minus the volume of the cylinder, but you see the issue, right? Here, right at the top, you have this little cap that if you do volume of a sphere minus volume of the cylinder, you're forgetting that cap, which is very important, and you get the wrong answer. So instead of doing one minus the other, what we're going to do is we're going to set up the volume between the two. So what is the volume? First of all, you recognize that there's some symmetry, right? Whatever happens on top is going to happen on the bottom as well. So I'm just going to take the top half and multiply by 2. So if I'm just doing the top half, I'm looking at the volume underneath the cylinder, underneath the sphere. Right? This is z equals 16 minus x squared minus y squared. This top portion here. Right? So I'm looking at the volume underneath this. So that's going to be my integrand. And what what is the domain? The domain is the stuff between these two circles, right? For any point between the two circles, you bring it up to Z, right? Or if you've described Z and you project onto the XY plane, you get the stuff between the two circles. So in the XY plane, this is the stuff between the two circles, one of radius 2 and the other of radius 4. Which you can set up in terms of x and y, but again, as we saw yesterday, you'd have to break it up into 4 pieces. Not going to do that. Instead, we're going to switch to polar. So you know the polar coordinates. X is r cos, y is r sine. So here you've got x squared plus y squared. And you know, we've seen that many times. X squared plus y squared is really r squared in polar coordinates. Jacobian, r, dr d theta, where r varies from 2 to 4. And theta, right? I mean, if you have this line segment and you spin it around, it will cover the whole domain, 0 to 2 pi. Yishen is asking if you can picture the XY plane and then start from there. So it's like the ring problem from yesterday. That's exactly it. It's exactly that. All right. And now you see the integration is trivial. Here, you would have had to break it up into 4 pieces. And this integration, you would have had to do a trig sub. It's so much work. The radius of the sphere is always the same, right? Because the radius of the sphere is this. And the radius is always 4 for your sphere. But that's not what we're talking about. Here we're looking at the volume underneath this function. So that's what's happening. You can integrate that with relative ease, right? There's no theta anywhere, so let's integrate it with respect to theta, 4 pi. And you see your Jacobian is saving you from having to do a trig substitution here. The integration is very easy as well. And we get negative 1/3, 16 minus r squared to the 3 over 2. Is that correct? And that is 32 pi over 3. Why do we multiply by 2? Because I only consider the top half, right? I'm only looking at the top half with the understanding that the bottom half is the same. There's some symmetry. If you prefer, the bottom half is the negative square root. So if you do top minus bottom, because we're looking at the volume between the two, right? So volume of the top minus volume of the bottom, minus minus gives you a plus, and you get the 2 again. So either way, it's the same thing. Convinced? Why are the bounds for R always 2 to 4? It's the domain, right? The domain in the xy plane. If you take any point in this annulus, then you bring it up to the sphere using that. So that's, this annulus here is really the domain. Quinn is asking a question, why don't we do that? Yishen is asking, if we directly draw the ring, then how does the cylinder differ from the sphere? Well, that's the thing, right? You cannot start with the ring because you don't know. And Raquel is asking, should we integrate from 0 to pi instead of 2 pi since we're only looking at the top half? No. No, because your domain is this whole thing. It's this function which determines the top half versus the bottom half. If you only did from 0 to pi, you would only be considering this half of the top half of the sphere. So we don't want that. We want the whole thing. Back to Blue Pill's question, though, why are the bounds for R always 2 to 4? Again, right, let me redraw it before we leave this question. You have a sphere, and you have a cylinder. And we're looking for the region between the two. We're looking for the volume between the two things. So imagine an apple that you've taken the core out. That's what we're looking at. And if you're looking at it from the top, a bird's eye view, right? A bird's eye view, what does it look like? Well, you've got this core that you've removed. This is the bird's eye view. Right? So that's your domain. The stuff in between here. That's your domain. And if you take any point in this domain, which is this right here, right? If you take any point, then you're going to bring it up to the sphere using your equation of the sphere. So what we're looking at is the volume underneath the sphere, but restricted to this domain. It's this idea of projecting that we were doing originally, but it's the same thing, right? This bird's eye view, that's your domain. Convince yourself, right? Take any point in here, you bring it up to the sphere using this. 32 pi. Have I made a mistake? This is 4, sorry, yeah. When x is 2, this is 4. 16 minus 4 is 12. Sorry. So that is 2 root 3, where I just treated it as 2. So I'm missing a 3 root 3, which is 32 pi root 3. Is that what you have? Yeah, there it is. Yeah, I just made a mistake plugging in 2. Somehow I was treating this whole thing as 4 when it's in fact 12. Thank you. So Yishen is suggesting a bird's eye view can only help us to set up the domain. Indeed. We still have to set the entire question in 3D. In fact, indeed, we have to, yes. Right? I mean, we're setting it up in 3D to understand that what we're looking for is the volume underneath some function. Isn't the R different as you go up or down the z-axis? Well, that's the thing, right? The R is measured from the origin going outwards. So once you've settled on your domain being this, and you're describing this in polar coordinates, the R isn't going up, right? The R is not going up anywhere. If you take any point in here, you're going to bring it up to the sphere using that. But that is right here, has no bearing on R. Well, that's right. I mean, Ranjit, R goes from 2 to 4 everywhere. Right? 2 to 4 throughout. So as Tony points out, the circle is only used to restrict bounds for R of the integral. Does this method account for the caps? Well, again, remember that we're not subtracting here. We're not subtracting. So I'm not even looking at this business inside. I'm doing the outside. I'm doing the outside, so we're good to go. We don't have to worry about caps. We don't have to worry about anything. Ahmad's asking, what if we weren't dealing with a circle? Well, that's where you have to adapt. And Blue Pill is saying R lives on the domain and is associated with the z value for a function. Exactly. Exactly that. What if it was a rectangular box? Well, I mean, again, let's look at Brun's question, and that'll give us an idea of what can happen. Let me scroll back up here. X plus y plus z. So I'm going to guess that the question is asking to find the volume enclosed by these things. What are these things? These 4 objects are what? What kind of objects are these? You tell me. Axes, planes. Planes are the right answer. Thank you, Ranjit. X equals 0 is the YZ plane. Y equals 0 is the XZ plane. Z equals 0 is the XY plane. And then you have this plane, which is that. So when x is 0, this is just a straight line coming down. When y is 0, it's just a straight line coming down. And when z is 0, it's just a straight line. So there you go, you have this. Is that a prism or something? I don't know. Whatever. But there it is. So what are we looking for? We're looking for the volume inside this thing. Everybody with us? And we're looking for the volume inside, or in other words, the volume underneath this plane restricted to this region. Right? For any point in this region, you bring it up to the plane using this equation. For any point in here, you bring it up to your plane using this function. So the volume is the volume underneath this function restricted to this triangular region T. That's the volume. Now, how do you describe T? How does y vary? If you decide you want to integrate with respect to y first, how does y vary? Y goes from here to there. Y goes from 0 to 7 minus x. Once you've described y, you project onto the x-axis, and you get the interval 0 to 7. Thank you, Ben. 0 to 7 minus x, and then 0 to 7. There it is. Integration is trivial, so I'll let you work that out, but there it is. Let's do one more. Same question. Find the volume bounded by Maud is asking what chapter we are on. I don't know. I don't know. But I mean, look, it's polar coordinates. It's polar coordinates in double integral. Take a moment and graph this. To understand what's happening. So z equals 6 minus x squared minus y squared. Chapter 15, thank you, Chris. We're going to graph it in the xz plane when y is 0. This is just a parabola coming down. And when x is 0, in the yz plane, this is still a parabola coming down. And how do you put this together? Well, when z is c, bring this to the other side, you get x squared plus y squared is 6 minus c, which are circles. So you put this together using circles. So you have this dome shape, this paraboloid, and then do the same for this. Well, when y is 0, this is a parabola coming up in the xz plane. When x is 0, this is a parabola coming up in the yz plane. And again, if z is c, you get circles. So you see what's going to happen, right? They're going to intersect at some point, and we're looking for the volume between the two. And the domain, right, the projection of this onto the xy plane, the bird's eye view, is going to depend on what the intersection actually is. So let's work that out right now. What is the intersection? If you bring this over to the other side, you get 3x squared plus 3y squared is equal to 6, or x squared plus y squared is equal to 2. You get a circle of radius root 2 here. So the projection onto the xy plane is a circle of radius root 2. If you were looking from a bird's eye view perspective, you would just see a flat disk. Right? Or again, convince yourself for any point in here, right? You bring it up to these two functions, and we're looking for the volume between the two. So it's going to be volume of the large minus volume of the small. Inside this domain. So which one is the large function? Which one is the small? First one we drew, paraboloid coming down. That's the top function. So top function minus the bottom function. dy dx, say, where your domain is a disk of radius root 2. X squared plus y squared less than or equal to 2. Convinced? How are we doing here? Well, I mean, you've got options. You can integrate dy dx, right? You know how to describe this domain in x and y. Y is going to go from the negative square root to the positive square root, and x is going to go from negative root 2 to root 2. That's fine. And, you know, integration with respect to y is easy enough, but once you do the integration and you plug in, now you're going to have square roots It's your radius that is square root of 2, right? X squared plus y squared equals r squared. So, I mean, convince yourselves that integration with respect to y, easy, but then you're going to plug in the square root of 2 minus x squared, and then it's possibly going to be difficult. Instead, we're going to switch to polar. Right? Because we're dealing with a disk here. So that's easy to describe in polar coordinates. Plus, we have this nice x squared plus y squared happening, which is also very convenient for us. So if we switch to polar, this x squared plus y squared is just r squared. So this is 6 minus 3r squared. Jacobian dr d theta. Where r, right, now you want to describe your disk in polar coordinates, r varies from 0 to root 2, and then you swing that around, 0 to root 2, and you swing that around 360 degrees, or 2 pi. There it is. I'll let you integrate that. That's simple enough. Questions here? Let's discuss a few nice applications, well, really just one. Suppose you've got a Ran is asking this question in dy dx is difficult because you've got to break up the circle into 2 functions. Well, not only that, but what would be your bounds? Y would go from the negative 2 minus x squared to positive 2 minus x squared, and x would go from negative root 2 to root 2. And like I said, integration with respect to y, easy enough. So that's 6y minus 3 x squared y minus y cubed, where you are between this and that. And if you plug in just this one part, the next step is going to be to integrate 2 minus x squared. And you know how to integrate that. This calls for a trig substitution. In fact, a sign substitution. And then here, you're going to have x squared times the square root of 2 minus x squared. So once again, this calls for a trig substitution. And here, you're going to have a 2 minus x squared to the 3 over 2, which calls for another sign substitution. So, I mean, you're going to have to make 3 sign substitutions. It's a lot of work. So Fubini is suggesting polar coordinates are only useful when we deal with circles, spheres, or cylinders. I mean, they're particularly useful in that case. It doesn't have to be that, but they're very well equipped to dealing with that. Yining is asking why use one function minus the other. Where are you referring to that? I'm not sure which. Do you mean here, one function minus the other, or do you mean from the negative square root to the positive square root? I'm going to give you a moment to answer. Any other questions in the meantime? Function of volume, well, that's the thing, right? The volume is, what we're looking for is the volume between two functions, right? That's why we graphed them, to understand what was happening. And we had one of them a paraboloid coming down, and one of them a paraboloid going up. So this was the volume we were looking for, the volume between two functions, right? So we did volume of the top minus volume of the bottom. In very much the same way that when you're looking for the area between two functions, you do area of the top minus area of the bottom, right? Integral of the top minus integral of the bottom to get the area between the two. Exactly the same thing here. Now let's consider a nice application. Suppose you have a solid of varying density. Right? Density described by some function. Then the mass is just the integral of the density over your region. Right? Because the integral is really a sum, right? So you're adding all of these densities together to give you the mass. Moreover, let's discuss the center of mass, which is a point on your object where you would balance it so that it doesn't rotate under the pull of gravity. This is the center of mass. See what I'm doing here? I'm balancing it with the one finger. That's the center of mass. The center of mass is a point which we can count. So the center of mass is a point, usually denoted x bar, y bar, where x bar is the double integral over the region of x times the density over the mass. And similarly for y bar. In the case that the density is constant, the center of mass is called the centroid. Yeah, it's called the centroid. And notice that over the mass, which would have been this, and you can factor out the c's. And the c's just cancel out. So this would have been just the double integral of A over the double integral of 1, which you know to be the area. Same for y bar. That's x times rho. Absolutely, Yishan. X times rho. Let's take an example. Let's graph this, see what's going on. Y equals 0 is the x-axis. Y equals 2x, straight line through the origin. And this thing, which we will conveniently rewrite as 1 minus x over 2. Starts at 1/2 and is coming down. So what is the region we're talking about? The only region that has these three things, the only finite region is this. Where this is 1, and the point of intersection, shall we work that out? 1 minus x over 2 is equal to 2x, or 1 minus x is equal to 4x, or 1 is equal to 5x, x is 1 over 5. So they intersect at 1 over 5, and when x is 1 over 5, y is 2 over 5. Everybody with us here? Questions? All right, why don't we start by finding the mass? And let's understand what is happening here, right? You've got this density function, which is x. So, you're starting out here with no density, and as x increases, the density is getting larger and larger. So it's an object that doesn't have any density here, but it gets more and more dense as the x increases. So, without too much thinking, we're going to expect possibly the center of mass to be somewhere in here. People having issues with the audio? I didn't check yesterday's video, but I'm going to assume that it never stopped. Some people were reporting issues, but all right. So anyways, imagine trying to balance this object on a finger where it's heaviest around here. You're going to expect the center of mass to be somewhere here. We were going to calculate the mass, which is the double integral of the density over the region. Thank you, Ahmad. Now we have to determine if we're going to integrate it with respect to x or y first. Your thoughts here? I claim we're going to want to integrate with respect to x first. Why is that? Varies. Y goes from here to there for a while until you hit 1 over 5, and then it goes from here to there. So if you integrate it with respect to y first, you're going to have to split it up, as Brun suggests. However, if you describe how x varies, x goes from here to there always. So you're just cutting down your work by that much. X goes from y over 2 to 1 minus 2y. Once you've described how x varies, we project to the y-axis, and you get 0 to 2 over 5. Integrate with respect to x. It's easy enough. Integrate again. Minus 1 over 6. Finish it up. Why? So Chris is asking, why is the mass x dA? We were given the density right here. I haven't erased it yet. So the density was given to be x. So the mass is the integral of the density. Let's finish that up. Next is 2 over 5. When y is 2 over 5, this is 4 over 5, so that's 1 over 5. Minus 1 over 6. That's 1 over 5 cubed. And that is 8 over 12 times 5 cubed. Subtract, plugging in 0. So you get a plus 1 over 6. Is that anything good? I don't know what that is. Let's call that M. Let's call that M for mass, unless I made a question. No, unless I made a mistake. And the x coordinate of the center of mass is going to be 1 over m times x times the density. Two over 25? Okay, I'll believe it. That works out nicely. 2 over 25. So this is going to be 1 over that. Thank you. Times this, or 25 over 2, x squared dy dx, where again y varies from this to that. That's not what I mean at all. X varies from there, and y from 0 to 2 over 5. I feel we should evaluate this, only to point out, right, I was suggesting that the center of mass should be bigger than 1 over 5, so it should be somewhere in here. Let's see. Let's see if that makes sense. So this is 1/3 x cubed. Why don't I take the 1/3 out? 1/3 x cubed. Y cubed over 8. And integrate again. 25 over 6. This is negative 1 over 8. 1 minus 2y to the 4 minus y to the 4 over 32 from 0 to 2 over 5. All I'm saying, without finishing this calculation up, I'm suggesting that this should be bigger than 1 over 5. Probably, I don't want to make any predictions there, but for sure we expect this. And what do we get? That's 1 over 5 to the 4. That's 16. So that is 1 over 2, 5 to the 4. Subtract, plugging in 0, you get a plus 1 over 8. What do we get? Common denominator of 8 times 5 to the 4. Here we get a minus 1. Here I get a minus 4. And here I get a plus 5 to the 4. So this and that cancels. And the numerator, if I factor out a 5, I get a 5 cubed minus 1 over 6 times 8 times 5 squared. I'll cancel one of these. 25, 125, 124 over 6 times 8 times 5. 124 is, no, is 4 times 31 over 8 times 6 times 5. So 31 over 60, there you go. A bit more than half. 31 over 60, anybody? Yushen is asking, how can we expect that? You have, I mean, we graphed the region, right? The region looks like a triangular region where, and then when you look at your density function, which is x, the density is increasing. So here, very little density. When x is 0, there is 0 density. And as you increase, you get more and more dense. The object weighs a lot more as you get closer and closer to 1. So the idea is, imagine this object in your hand. Where would you balance it? You wouldn't think that placing your finger here, since this is very heavy, it's going to topple over. You're going to want to place your finger somewhere in here. And that's exactly what this is telling us. But that's just the x-coordinate. For the y-coordinate, right? So the x-coordinate, I mean, my picture is not to scale here. Really should be more like this. So here is 31 over 60. Unless that's incorrect. Martin seems to say 2 over 25. Have I made a mistake? And then you, right, so the x coordinate of the vertex is here. You're going to calculate the y coordinate, maybe somewhere, well, probably on the lower end, maybe somewhere around here, right? You still need to calculate. I'll let you do that. Calculate y bar, but you can do that, right? So what you get is a point xy where you can balance that object. How are we doing? Questions here? Questions about the center of mass? Questions about the double integral? Because if there are no questions, we're going to move on to the triple integral. Anything? Anybody? No? We're good? Triple integral it is then. Well, it's the same. It's the same as the double integral. It's an immediate generalization where instead of integrating over a domain, thank you a lot, instead of integrating over a domain in the xy plane, you're going to integrate over some 3D region. And then you've got some function. W equals xyz hovering around in some fourth dimension. And we're looking for the hypervolume between the two. That's it. In the same way that the whole point of the double integral wasn't to learn how to integrate again, because you know how to integrate, but rather it was the setup that's important. It's the same thing here. It's the setup that's important. And how do you set things up? You set them up in exactly the same way that you were setting up a double integral. In a double integral, you look at how one variable changes, and then you would project onto the other variable. Here you're going to describe how one variable changes, and you're going to project onto the remaining plane defined by the other two variables. And so on and so on. Asimov suggests Fubini's theorem extends immediately. So triple integral dv, v as in volume, as opposed to the double integral dA, A for area, right? Because double integral, you're integrating over an area in the xy plane. Triple integral, you're integrating over a volume in 3 space. So what is this? This would be f, maybe dz, dy, dx, but by Fubini's theorem, you can interchange any two that you want. So in this case, you have 6 possibilities. Not just 2 as in dy dx or dx dy. But here you can say dz dy dx, or dz dx dy, or dy dz dx, or dy dx dz, or dx. I mean, you see what's going on there. You have 6 possibilities. Which one comes first? You have 3 possibilities. Which one comes second? 2 possibilities left. And which one comes last? Only 1 possibility. 3 times 2 times 1. I know what you're thinking. Oh, my connection is unstable. Did it cut? Did something stop right now? I just had a message that the connection was unstable. So maybe that's what, yeah, it did lag. There you go. Maybe that's what happened last time. To some people, maybe my connection was unstable. I mean, it seems to very well. Yeah. I mean, that message has just come and gone. There you go. Okay. What was I going to say? Yeah. So I mean, I know what you're thinking, right? 4-dimensional hypervolume. Does this have any implications? An excellent question. Notice that in the one variable case, if you were integrating a function that is 1, you get the area of this rectangular box, but really the length of the function, of the interval. In the 2-dimensional case, we use this already. If you're integrating over domain D, a function which is always 1, you get a volume, but numerically it's the same as the area of D. And in 3 space, if you integrate a function which is 1 over the whole thing, you get the volume of your region. So an immediate application is volumes, which you might have been able to set up just as a double integral anyways, but you can also set it up as a triple. Cecilia's asking if we're able to simplify integrals here. With being a 4th dimensional, it's hard to visualize. Indeed, a 4th dimension is hard to visualize, but here's the thing. We don't really care about the function hovering above, right? All we care about is being able to describe the region we're integrating over. The only thing we're interested in is being able to set up the integral properly. So in the same way with a double integral, where we were just integrating over the region, and it's that region that we had to describe properly, same thing here. So we never need to graph the function hovering above in a 4th dimension. Yishen is asking if we consider the first 2 variables first and change to a double integral plus a single integral. That's not always possible. It's possible sometimes, but seldom. So in general, this cannot be done. Ranji, absolutely. A triple integral is skipping a double integral and straight up jump from 1 degree integral to volume. Well, I'm not sure why we're jumping a double integral there, right? Because it is a triple integral, so it's really 1 integral more than the double. So it's an immediate generalization, right? In the same way that the single integral generalized to double, double generalizes to triple, and so on and so on. Let's take some examples. Before we do that, let me mention that this idea, right, again, I know I've discussed it, but it's what's really important here, right? How were we describing our region D? We described how one variable varies, and then we would project onto the remaining axis. Here, that idea of projection becomes doubly important because it's difficult to see sometimes. You're going to describe how one variable varies, and then you project onto the remaining plane. Let's take an example of that. Ahmad is saying volume is three-dimensional, so we need three integrals, but we saw that the double integral of a function actually represented the volume underneath that function, right? The integral of a function, single integral, represents the area. So you actually don't necessarily need a triple integral to represent volume. And in fact, a triple integral represents a hypervolume, a four-dimensional volume. But if your integrand is 1, numerically, it's the same as the 3D volume of the region. Let's take a few examples to illustrate All right, here it is. Take a moment and graph this. It's important to understand what we're working with. You can graph this with relative ease. Right, and again, we're not graphing the integrand, right? Here, the integrand, w equals y minus x, you have this function hovering above in some fourth dimension. Well, we don't care. What we care about is the region you're integrating over. Start with the first one. Z equals x squared minus 1. You know what that is. In the xz plane, it's just a parabola coming up. Right? It's really z equals x squared, but 1 down. In the xz plane. And now there's no y mentioned here. So you understand that it's that same parabola for any value of y. So think of dragging this in the direction of y. There it is. And the other way as well, right? It goes both ways. And then you have this, which again is a parabola, but now coming down in the xz plane. And again, there's no y mentioned. So drag that parabola in the direction of y. So you see what's going on? Right, you've got one parabola here and another parabola there. There it is. That's what we're looking at. And then you're cutting it with y equals 0, y equals 2. These are two planes. The yz plane, and then this y equals 2 plane right there. So there it is. That's what we have. Perfect. And again, you now have this function hovering above in some fourth dimension, and we're looking for the hypervolume, right? Because I mean, you could do a Riemann sum argument, right? Where this is delta x. No, that's actually delta y. Delta x is right here. Delta x, delta y, delta z. And then you pick a point and you look at its image. So you draw a four-dimensional box of height, f of xi star, yj star, zk star, delta x, delta y, delta z. And then you add all of those up over I, j, and k, and you get a Riemann sum. And as delta x, delta y, delta z gets smaller and smaller, this gets closer and closer to this business. The volume underneath the function restricted to your domain. Right, so the whole idea of Riemann sum extends and everything, but again, the point being that we don't really care too much about this function because we wish to set the integral up properly. So now we have to decide, how are we going to set it up? We have 6 possibilities, dz, dy, dx, or any of the other 5. It's up to you. Let's set it up, dz, dy, dx. See what happens. How does z vary? Z is measured this way. And we're talking about the region in between these two parabolic cylinders. So you see what's going to happen, right? Z goes from the bottom cylinder to the top. Z goes from the bottom, right? I mean, if you look at what we were what we had before. We were looking at this. And Z is measured this way. So if I bring it to you here, you see Z is measured this way. Z starts in the white and goes all the way up to the pink. Yeah. So you see what's happening, right? Bottom parabolic cylinder, which is this one. So Z goes from x squared minus 1 to 1 minus x squared. And now that Z has been described, we want to project to the xy plane, to the remaining plane. So what is the projection? What is the projection onto the xy plane? If you're looking at this from a bird's eye point of view, and of course you understand that we're stopping at the intersection, right? So this extra piece there isn't really there, right? But from a bird's eye point of view, what you have is a rectangle, right? What you have is a rectangle. Let's figure out where these two things intersect as far as x is concerned. Where do these two things intersect? X squared minus 1 is equal to 1 minus x squared. So you get 2x squared is equal to 2. So x is easily seen to be plus or minus 1. And y, well, y was set to go from 0 to 2. So y goes from 0 to 2, x goes from minus 1 to 1. Absolutely. And there you go. Integration is trivial. Let's integrate. Let's integrate. Integration with respect to z, there is no z. So that's x minus y times z. Plug in. What do we get? X minus y times 1 minus x squared minus x minus y times x squared minus y. Let's expand this. This is x times 1 minus x squared minus y plus yx squared and minus x times x squared minus 1 plus yx squared minus y. Excellent. Why am I doing it this way, you may ask? Well, it's to observe that x is the region of integration for x is symmetric about 0. And this is an odd function of x. So this is going to integrate to 0. And this is an odd function of x. So that is going to integrate to 0. So I can forget those already. And now I just have the same thing twice. So that is 2yx squared minus y. So that, well, I mean, maybe I can factor out a y, in fact. So that's y squared between 0 and 2, which is 4 1/3 x cubed minus x between -1 and 1, which is minus 2/3, so minus 4 minus 16/3, apparently. Well, so this is the volume of this four-dimensional object. Well, I mean, of course, you recognize that it's a negative answer, right? So it's a volume if the function is positive, and if the function is negative, it's the negative volume in the same way as if your function is above the x-axis, then the integral is the volume underneath the function, but if your function dips down below, then it's negative of the volume. So now what if you have both positive and negative things, as is probably the case here? Then, you know, it's a mix of the two things. Ahmad is asking if the triple integral is the last of the multiple integrals. Well, it's the last one we're going to see. But of course, it extends to how many integrals you actually want. So there's no reason to stop at 3. You can go 4, 5, 6, and so on. It's all the same. So Quinn is asking, it's really the absolute value. What is the absolute value? You mean if you integrate the absolute value of the function, then you get the area underneath, yes. Ranji would like to go back to this x times 1 minus x squared integrating to 0. The region of integration here, right, if you were to graph that in the xy plane, x goes from -1 to 1. Y goes from 0 to 2. So we're integrating over this square, which is symmetric about the y-axis. So for every point xy in here, you have a corresponding point, negative xy, on the other side. And now look at your function, which is x, 1 minus x squared. In here, you have a positive value, right? You're going to have some positive height, x, 1 minus x squared. Over here, right? So your function at the point xy is this. and your function at the point negative xy is negative x, 1 minus negative x squared, which is negative 1 minus x squared. So you see the signs are just the opposite. So if here you have a positive height, over there you're going to have a negative height, and they're going to cancel themselves out. Yishan, if the question is asking for volume, you know you're expecting a positive answer. So if the question was asking for volume and you got a negative number, you know you did something wrong. I didn't erase this yet because I wanted us to set it up just for fun. Let's set it up differently. What if we describe how y varies first? How does y vary? Y is measured in this direction, and we were actually given how y varies, right? For any point xz, y starts at the xz plane and moves all the way until it hits this plane, the y equals 2. So y actually goes from 0 to 2. Unencumbered, if you will. And now that we've described the y variable, right, again, look at it this way, right? Y, it's like this. So this is how y varies. And if you look inside, you see y varies from 0 to 2. But then when you project onto the xy plane, right, think of squishing this. I mean, did I say xy? I meant xz. Right, to describe how y varies, project this object onto the xz plane. What do you get? You see what you get there? When you project onto the xz plane, you get this region. Let's graph it here. This is xz. You get this region right here. You get this region in the xz plane. So now you would describe how, I mean, you decide what you want to do. I think it's going to be easier to say dz dx, because if you say dx dz, you're going to have to break it up into two pieces. Whereas z always goes from the bottom parabola to the top. So z goes from the bottom, which is x squared minus 1 to 1 minus x squared. And then once z has been described, you would project onto the x-axis, and you get negative 1 to 1. All right, consider this. Take a moment and graph that, see what's going on. You know what's going on. So the origin, x is 1, y is 0, z is 1. So x is 1, z is 1. X is 0, y and z are 1. So this, I should label these. And finally, both x and y are 0, but z is 1. All right. There it is. So now you have to decide what you want to do. Which variable do you want to integrate with respect to first? You have options. You can do whatever you want. You have 6 possibilities. They're all just as easy, I think. Let's set it up a few ways. Why don't we do dz, dy, dx first? And then we'll set it up a different way. Maybe we'll set it up dy, dx, dz. Just for fun. Right, I'm sorry, Renji and Ahmad, what's going on? Have I made a mistake? I'm suggesting dz, dy, dx. Let's set it up, dz, dy, dx. How does z vary? Right? We're talking about the inside here. Z is measured this way. So how does z vary? I claim z is going to start in this triangular plane and go all the way to this top business. Do we see that? Right? Z is going to start in this triangular region and go all the way to the top. Well, not 0 to 1, right? Because if you say 0 to 1, if z goes from 0 to 1, z would have started in the xy plane and gone all the way. So in fact, this top is the plane z equal to 1. But it doesn't start in the xy plane. Rather, it starts in this slanted plane. So we need to find the equation of that plane here. What is that plane? Well, that plane has these two vectors on it. So you know to describe a plane, you need the normal vector. And if you've already got two vectors there, all we need to do is find the cross product. And there you have it. So this plane right here, this slanted plane, has equation minus x minus y plus z is equal to d, where this goes through the origin. So d has to be 0. It also has to go through these 2 points. So you can check, right? Minus 1 plus 0 plus 1 is 0. And same for the other one. There we go. Very nice. So that's the equation of that plane. So z goes from this slanted plane, which is z equals x plus y, to the top plane, z equals 1. Now that we've described how z varies, we project onto the xy plane. So squish this down to the xy plane. What do you get? What is the shadow cast by this object on the xy plane? I claim it's this triangular region. Essentially, this triangle here, but in the xy plane, where this is x equals 1 and this is y equals 1. So how does, if we're looking at this, how does y vary? Y goes from, again, this is increasing direction for y. Y is measured this way. So y goes from here to there. Y goes from the x-axis to that line. And I think you know exactly what line that is. That is the line y equals 1 minus x. Right? It goes through the point 1, 0 and 0, 1. So 0 to 1 minus x. And then once y has been described, we project onto the x-axis to get 0 to 1. How are we doing? For fun, let's set it up dy dx dz instead. Actually, let me switch that around and let's say dz dx. So let's say dy dz dx. Renji is asking, and Yining as well, how you get the boundary for z. Well, I mean, you have to look at your picture. So pictures become very important here. and you ask the question, how does z vary? And for any point xy, first of all, this is the increasing direction for z. This is how z is measured, right? So if you take any point xy, z starts living as soon as you hit this slanted plane, and you keep going until you hit the horizontal plane. So Ranji is asking why we need to find the z plane. I suspect you mean this one. Well, that's exactly because that's how z behaves. Z goes from this plane to that one. Let's describe how y varies. Perhaps we'll be able to see the relationship. How does y vary? Y is measured in this direction. So for any point xz, y starts living when you hit this side plane. So y equals 0, the xz plane, and it keeps going until you hit this triangular plane right here, namely this plane again, which is z minus x. So very nice, Yishan, minus x plus z. And once y has been described, then we would project everything to the xz plane. And I think it's easy to see that we get this triangular region in the xz plane. Right, this region right here, where this is z equals x, and this is z equals 1. Prin wants us to reconsider how y varies, right? So pick a point xz and go in a increasing direction for y. This region starts when you hit this plane on the side. This is a plane in the xz plane, in other words, in the y equals 0 plane. So it starts living here, and then you continue until you hit this side triangular plane, which is this. And it's always like that, right? No matter where you start, the region starts living when you hit the side plane. And, well, I mean, no, it's going to be difficult to see, but, and stops when you hit the, this one here. And then once y has been described, we project onto the xz plane, and we get this triangular region. Yishen is asking, does the first integral always have boundaries in terms of all other variables? Well, that's the general idea, absolutely. And then you lose, right? I mean, well, first of all, if you're integrating with respect to z, you don't want z's anywhere. So the bound should just be in terms of x and y. And then if you're describing y, then it should just be in the terms of the remaining variables, so that you don't get functions, but rather a numerical answer. Y the plane is the same for both dz and dy. And I suspect you mean this plane. Well, this plane never changes, right? The equation of that plane is always the same. It turns out that it plays a role in both how z varies and x varies, but it need not have been the case. Well, exactly, Tony. Your explanation is exactly it. It's the base for z, right? So it's the lower bound for z, but it's the upper bound for y. Absolutely. So once we've described how y varies, we project onto the xz plane. And now how does z vary? Right, again, z is measured this way. So z is going to start here and go all the way to there. Or if we're looking at this, z starts here and goes all the way to there. Z goes from x to 1. And once z has been described, we project onto the x-axis. And we get 0 to 1. Shall we integrate both of these just to make sure that we get the same answer? It's a nice exercise. Right, because you know we never actually proved Fubini's theorem. But we can convince ourselves by evaluating these integrals. So let's integrate, let's evaluate the first one. You're integrating with respect to z. So you get 1/2 x z squared dy dx. Integrate with respect to y. Integrate with respect to y. When y is 1 minus x, this is just 1, so minus 1 over 6x. And when y is 0, this is x cubed, so x to the 4, plus 1 over 6x to the 4. So this is 1/3. So 1/3 x. So 1 over 6x squared minus 1 over 6x cubed plus 1 over 30 x to the 5, 0 to 1. This is gone, and you get a 1 over 30. Okay, and let's do the other one just to see that we get the same answer. Integration with respect to y is trivial. So this is x z minus x dz dx. Let me expand it. This is x z squared minus x squared z. So 1/3 x minus 1/2 x squared. When z is x to the 4, and 1/2 x plus 1/2 x to the 4. And once again, this is 1/6. Is it the same? 1/6 x to the 4, 1/3. Yeah, so it's the same. It's exactly the same. That usually does not happen, but now it's the same. So you know it's the same answer. Very nice. Very nice indeed. If we're asked to calculate a volume, 1/30 will be the volume. Well, yes, hypervolume in this case, yes, absolutely. Because your function was always positive, right? It was a function xz, which lived in a region where x and z were positive. So yes. Why is it not always the same? Why is it not always the case if the answers are the same? Well, I mean, just look at a double integral. Sometimes by changing the order of integration, you get two things which are completely different. Or if you just look at the single integral, if you integrate with respect to x or with respect to y, sometimes you're able to do both. And the integrands are completely different, but the result is the same. And that's what you often get. But in this interesting case, the integrand is exactly the same. If you were so Yishen, if you were looking for the volume of that shape, you would just have integrated one and get the same boundary. Very exactly that. Yes. Let's do one more. Quinn is asking, is there a rule or pattern for the results to be the same? Well, Fubini's theorem answers that question, right? Fubini's theorem says that you can integrate any way you want. And as far as this course is concerned, it will always be true. We saw the condition for Fubini's theorem to be true, namely that the integral of the absolute value should be finite. And there are examples where the integral dy dx is not the same as the integral dx dy, but we're not going to discuss those. As far as we're concerned, you can always interchange and you're good to go. In other words, the hypotheses of Fubini's theorem are always satisfied. Let's consider this example. Consider this. Let's graph that, see what's going on. So the first one, y squared plus z squared equals 9. What is that? Let's graph that in the yz plane. You know what that is. You recognize that. This is the equation of a circle. A circle of radius 3, centered at the origin in the yz plane. And no axis specified. So it's that same circle for all values of x, right? When x is 0, and then when x is 1, when x is 2, when x is 3. So you have this cylinder coming out towards us along the x-axis. X equals 0 is the yz plane, right? Because I mean, it's an infinite cylinder that goes both ways, right? So it's infinitely long in both directions. But now we're cutting it at the yz plane. We're cutting it with y equals 3x. What is that? Well, again, in the xy plane, this is just a straight line. But no z is specified once again. So it's that same straight line when z is 0, when z is 1, when z is 1 over 10, when z is 1/2, and so on. You're stacking these straight lines in the direction of z. What do you get? A plane. This is a plane again, right? It's the equation of a plane, minus 3x plus y equal to 0. It's a plane in 3 space. Z equal to 0, which is the xy plane. And finally, first octave. All right, there it is. So you know what's happening. What region are we talking about? This, let me graph it again. There's too many things going on here. This plane all right, turned out better than expected. This is it. This is the region we're integrating over. And once again, we have this 4-dimensional function, w equals z, that we're integrating over. Z is always positive in this region. So without doing any work, we expect this integral to be bigger than 0. Certainly not going to be negative. All right. Well, now, I mean, you've got options. What do you want to do? We're going to set up the integral. Something, something, something. Right? You have 6 options. I think we're going to want to set it up dz, dy, dx. Maybe. I mean, there's no reason for that. Whatever. Let's set it up this way. We'll set it up a different way as well. What if we set it up the z dy dx? How does z vary? Z goes from the bottom triangle. Wait, the bottom triangle doesn't have a boundary curve. I'm not sure what you mean there, Yishen. The bottom triangle, right? This is y equals 3x. This is the part of the cylinder when it hits the xy plane. And over there is the plane x equal to 0. Well, I mean, let's set it up, dz dy dx, see what happens. How does z vary? Z goes from the bottom triangle to the top curve part. Bottom is z equal to 0. And this curve business is part of the cylinder. The top part, right, so the positive 9 minus y squared. Once z has been described, we would project down to the xy plane, and you see that you get this triangular region here. So exactly, Yineng, right? Yep, very nice. So once we've described z, we project onto the xy plane and we get this triangular region. How does y vary? Y goes from y goes from 3x. Y goes from 3x to y equals 3. Once you've described y, you project onto the x-axis and you get 3x to 3. And finally, 0 to 3. No, 0 to. It's a bit hasty there. 0 to. Right, this is the line y equals 3x. So when y is 3, x is really I think you know x is 1. Let's set it up dx dz dy instead, just for fun. 0 to 1, thank you, Raquel. Let's set it up dx dz dy. How does x vary? You know how x is measured. X is measured this way. So if you're moving along, x goes from the YZ plane. Can we repeat the y boundary again? Well, let's graph it here in the x, y plane. Once you've described z, you project onto the xy plane, and you get this region right here, where this is y equals 3x, and this is y equals 3. So when y is 3, x is 1, and this is the region we're integrating over. So how does y vary? Y goes from here to there. Y goes from this line to that line. Y goes from 3x to 3. What about x? How does x vary here? X goes from the yz plane, which is x equal to 0, all the way to this plane, which is x equals y over 3. Once x has been described, we project onto the yz plane. Squish this to the yz plane. What is the projection onto the yz plane? I think you see it. It's this quarter circle. How does z vary? This is the equation. Z equals square root of 9 minus y squared. So z goes from 0 to square root of 9 minus y squared. And once z has been described, you project onto the y-axis, and you get 0 to 3. We're out of time, but I'll let you evaluate both of these to convince yourselves that these are the correct bounds. The answers should be the same. And you can repeat in 4 different ways, setting up 4 different integrals, right? dz, dx, dy, dx, dy, dz, and 2 others. dy, dx, dz, or dy, dz, dx. And integrating each of these 6 different integrals should yield the same answer. So this is very nice. First of all, it gives you an understanding of how to set these up, and it reinforces the fact that you've done it properly because the 6 answers coincide. If we take a step back and you recognize that this is a quarter circle here, the question arises naturally. Do polar coordinates play a role in triple integrals? We'll see that tomorrow. Questions in the meantime? Anyone? How are you doing with this? So, well, let's say this, tomorrow's Thursday, and we're going to do change of variables in triple integrals. I don't think we're going to have enough time to discuss curves tomorrow. So I'm not going to post a new web work. So we'll only have 3 web work assignments. That'll be it. We will discuss curves on Monday, possibly a bit on Thursday as well, but not enough to post an assignment. Questions? Anybody? If there are no questions, I'll see you tomorrow. Can we quickly go through bound of day? I don't know what that means. Perhaps you meant boundary? The bound of dy. How does y vary Are we talking about in the first one? I'll assume in the first one, we had described how z varies. Z went from the xy plane to your cylinder, and then we projected onto the xy plane. And we got this triangular region, which I have reproduced right here. So this is our triangular region in the xy plane. How does y vary? Well, y is measured this way, right? So if you fix an x, y starts when you hit this line, the y equals 3x, and you keep going until you hit y equals 3, right? The region starts when you hit y equals 3x and stops when you hit y equals 3. Y starts when you hit 3x and stops at y equals 3. The dy, oh, so something we did not introduce. Let's do it. You want dy dx dz. So how does y vary in this case? Well, so again, y is measured this way, right? This is the increasing direction for y. So if you're moving along, y is going to start here and end there. Y starts on this plane, this slanted plane, and goes all the way to the cylindrical side here. Y goes from the plane to the cylinder, which is the square root of 9 minus z squared, right? If you solve for y here, 9 minus z squared. And then you would project onto the xz plane. So you would project this onto the xz plane. I'm going to let you think about what that gives you. Yining, we will do more examples of the triple integral tomorrow. Yes. Anna Maria did not learn Kramer's rule in 133. Don't worry about it. Well, I mean, look, I was never a fan of Kramer's rule, but as I get older, I have an appreciation for it. What was going on? We had two equations, two unknowns. We were solving for dy dx and dz dx. So solve any way you want. You can use matrices. You can isolate for one, plug it into the other, and solve. It doesn't matter. The answer should be the same. That's the only important thing. Pun is asking, why don't we take the normal anymore for the plane equation? Are you referring to this plane y equals 3x? It was already given. It was already given. We didn't need to find the equation of the plane. It was already there. Tony is asking triangle. Indeed, yes, yes. The projection onto the xz plane is a triangle. Very nice. Very nice. Absolutely. Thank you all for coming. I will see you tomorrow. It's a nice exercise to finish that up, right? As Tony suggested, the projection onto the xz plane is going to be a triangle. You still need to set it up, though. We'll continue on with this tomorrow and talk about change of variables in triple integrals. See you then.